Okay, let's do another example subset construction. And this time it's going to be a little bit trickier an example. We're going to explicitly have to have a state that represents the set containing no states. So we're going to have a state in the DFA that represents the set containing no states in the NFA. That is the empty set. So if we have a look at this NFA here, it's not terribly hard to inspect what the language is going to be. It's going to have to start with a 1, then it can consume any sort of garbage, and then a 1, and then any sort of garbage, and then a 1. So it looks like the language is going to be, it has to have a 1, and then some alpha, and then a 1, and some beta, and then a 1. Where alpha and beta can be any strings you like. We can also write this as what's called a regular expression. If you've heard of a regex, a regular expression, which comes from the field of passing in input on a computer. That's where the word regular comes from, because the set of all regular expressions can describe exactly the set of all languages accepted by DFA. The set of all regular languages, that's where the regular and regular expression comes from. So if you're familiar with regular expressions, you can also write this language as a 1, and then 0 or 1, as many of them as you like, and then a 1, and then 0 or 1, as many as you like, and then a 1. So that's like the regular expression that corresponds with this NFA. If you don't know what a regular expression is, that's fine, don't worry about it, I just put it there for pedagogy's sake. So let's try to convert this thing to a DFA. And we're going to use the same abbreviated notation as we did before, writing like S02 really represents the set of states 0 and 2. Okay? So we first explore the initial state, S0, and we're going to see what it does under 0s and 1s. So if I'm in S0 and I see a 0, I can't go nowhere. So I go to the empty state, which I'm going to call SEmpty. If I'm in S0 and I see a 1, there's only one place I can go, S1. When I say S1, I really do mean the set containing S1, but I'm using this as like an abbreviation notation for it, okay? So just be careful. Everything in this table is really sets of states, not just states. We have to explore SEmpty. If I'm in no states and I read a 0, I can't exactly go anywhere, so I can only go back to, I go nowhere, right? So I go to the empty state. And if I'm in no state and I read a 1, I can't go nowhere, so I go to no state, which is SEmpty. Okay? SEmpty always goes to SEmpty. I haven't explored S1, so we better explore that. If I'm in state 1 and I see a 0, I can only go back to S1. If I'm in S1 and I see a 1, there's two places I could go. I could go to S1 or I could go to S2. So I make a new state S12 representing both of these things. I've already explored S1, now I've got to explore S12. If I'm in either 1 or 2 and I read a 0, where can I go? Well, if I'm in S1, I can go back to S1. If I'm in S2, I can go back to S2. So that means I can go back to S12. If I'm in S12 and I see a 1, where can I go? Well, from S1, I can go to S1, or I can go to S2. And then from S2, I can go to S2 or S3. So that means I can visit these 3 states in total. So S1, 2, 3. I already know where this state goes. Now I've got to explore this one. S1, 2, 3. If I'm in S1 or S2 or S3, and I see a 0, where can I go? Well, if I'm in S1, I can only go back to myself. If I'm in S2, I can only go back to myself. If I'm in S3, I can't go nowhere. So S1, 2. Same for 1. If I'm in either 3 of these states, and I see a 1, where can I go? Well, if I'm in S1, I can go to myself or to S2. If I'm in S2, I can go to myself or to S3. And if I'm in S3, I can't go nowhere. So S1, 2, 3. All the reachable states are explored. I don't need to go any further. So for example, S23 can never be reached, so I don't need to explore it. In the worst case, for n states here, this table could be 2 to the n entries long. But because sometimes not all the states are reachable, you need not explore them all. We got lucky here. In the worst case, there could have been 16 of these things. Okay? So now we have to identify the final states. The final states is any set of states that contains S3, because S3 is a final state. So here, only S123 is a final state, and we denote final states with an asterisk. So now with this table, I can draw the corresponding DFA. I just read off the states. There is 5 states. S0, S empty, S1, S12, and S123. And then you just fill it in. So if I read a 0, I go to here. If I read a 1, I go to here. If I read a 0, I'm trapped forever. If I read a 1, I'm trapped forever. So S empty will always be a trap state, no matter what. Because if you're in the set of no states, you can't go nowhere, right? So S empty will always be a trap state. For S1, see a 0, see a 1. For S12, see a 0, stay where I am. See a 1, go to S123. For S123, see a 0, double back. See a 1, stay where I am. And this is the only final state. So you can see how this DFA has got the exact same behavior as this NFA. Because I'm trying to recognize strings that look like 1, alpha, 1, beta, 1. So if I see a 0, I'm doomed immediately and go to the trap state. If I see a 1, then I can sort of gobble up alpha, reading zeros until I see the second one. And then I can gobble up beta until I see the third one. Then I can gobble up infinite ones. If I see a 0, well, I've already seen 2 ones, then I just go back to S12. So for example, if I have the string 1, 0, 1, 0, 0, 0, 1, 0, 1. So this is of this form, right? Because you can sort of segment it into parts like this. So 1, alpha, 1, beta, 1. Let's see what the DFA does. So 1, 0, 1, 0, 0, 0, 1, we're accepted, 0, we're rejected, 1, we're accepted again. Okay, so this looks like the same behavior as this, which is good, because that's what subset construction should do. So, given this NFA, here is the corresponding DFA with the same behavior. It's a bit more complicated, it's got more states, but that's the price you pay for determinism. You have to pay using extra states. And again, in the worst case, this thing could have had 16 states in the very worst, right? Because it could have had S empty, S0, S1, S2, S3, S01, S12, yada, 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 S12, 3, 0. So that's all the possible combinations. Thankfully, most of them weren't reachable.